Okay, so now the last two topics in the chapter were magnetic fields from a solenoid, which is basically a coil of wire, and the force between magnetic currents. So let's start off with a solenoid. So the equation for a solenoid is that the magnetic field from a solenoid is, we had two equations for it. Mu zero, again a constant, times the current, times the total number of times you wrap the wire around divided by the length of the solenoid, or equivalently, mu zero I times n, where little n is just the number of turns per length. So sometimes if you bought an electromagnet or solenoid in a store, it would tell you just the value for little n, which is going to be the total number of turns divided by the length. Okay, so we're told now that this solenoid is 75 centimeters long. So L is 75 centimeters. And of course, we're going to put that into meters, 0.75 meters. Produces a magnetic field of 1.3 Tesla, so B is equal to 1.3. When it carries a current of 8.4 amps, so I is equal to 8.4 amps. So if I look at my equation here, I can see the only thing I don't have is N, and that's what it's asking us for. So N is equal to question mark. So I've got B, mu zero is a constant, I, and L. I want to find N. So I need to rearrange that equation to solve for N. So I'm going to bring everything over to the other side. So first times by L. So B, L is equal to mu zero I N. Then to get N by itself, I'm going to divide by mu zero I. And then it's just plug and chug. All right, so B, 1.3, L, 0.75 meters. Mu zero, 4 pi times 10 to the minus 7, excuse me. And the current is 8.4 amps. So I get quite a large number, 9.24 times 10 to the 4. So that's 92,400 turns. So when you make an electromagnet, you have to wrap the wire around many, many times. So often they'll use a machine to do it, to make something. So this is when you made an electromagnet in grade school, you might have done it by just taking a wire and wrapping it a few times around a nail. If you want one that has a big magnetic field like 1.3 Tesla, you really have to wrap the wire around it many times. Okay, so now let's go and do the last topic, which was the force between two current carrying wires. So remember, if you have one wire and a magnetic current going through it, it's going to create a magnetic field. And of course, we know that the second wire, if it has a current in it, it's going to feel a force due to that magnetic field. So what we're told is we've got two power lines. Each of them is 250 meters long. They're running parallel to each other with a separation distance of 35 centimeters. M didn't come out very well. Let's do that again. And the wires carry parallel currents of 120 amps each. So they both have the same current. Let's just call it I. I1 equals I2, which is I, and call it 120 amps. What's the magnitude and the direction of the magnetic force that each exerts on the other? So let me just draw a quick sketch. So we've got two wires. They're carrying currents. Let's just make the currents go up to the top of the screen in the same direction. They're 0.35 meters apart between them. They're 250 meters long. So obviously that picture isn't to scale. And I want to know what's the magnitude and the direction of the force. Well, the rule that we had in class in the lectures is that parallel currents attract each other. So parallel attract, anti-parallel repel. So wire 1 and wire 2 are going to get pulled towards each other. So it's an attractive current. What's the size of the force? Well, the equation we had was that force per unit length is mu zero times I1, I2 over 2 pi d. So if I wanted to find the force is just going to be multiplied by L, mu 0 I1 I2 times L over 2 pi d. So if I look at all the numbers I have, mu 0 is a constant. I got the two currents are both 120 amps. I got the length. I got the separation. So now it's just plug and chug. All right, so I've got mu 0, 4 pi times 10 to the minus 7. The current 1, is 120, and that's the same as current 2. The length is 250 meters. And 2 pi in the denominator. And d is 0.35 meters. And again, before I put in my calculator, I just like to go ahead and cancel out the pi on the top and the bottom, so I don't need to throw that in my calculator. But if you're happy enough to do it, that's fine. So if I do that, I get 2.06. And let's see, I've got two significant figures, it looks like. So I'm going to say 2.1 is my force, and the units of force is newtons.